Okay, welcome to this Guideline Geo webinar on Transient Electromagnetics and the ABEM WalkTEM 2 that we've put on in collaboration with our German distributor, CDM Smith. So today we're going to talk about TEM. We're going to look at the theory behind the method. We're going to look at considerations we might make for setting up a system. And then we'll look at some case studies, followed by a brief run through of the ABEM WalkTEM 2, what it looks like, and what the options are for using the system in the field. My name is Jimmy Adcock. I am the product manager for the ABEM range at Guideline Geo. I've been with the company probably coming up to 7 years. I started off as an applications engineer doing customer training, sales support and customer support, and then took over the product manager role in 2020. For those who don't know us, Guideline Geo are a manufacturer of geophysical equipment. We make ground penetrating radar systems under the Marla brand and more traditional resistivity, seismic and TEM systems under the ABEM brand. As I said, we've put this webinar on in collaboration with our German distributors who are CDM Smith, and specifically Reinhard Schultz, who works there as a project manager and senior geophysicist. He's been in geophysics for quite a long time. I hope he doesn't mind me putting these stats up on the screen. Very well respected member of the geophysics community in Germany. So there's his contact details if you want to get in touch with him. And I will put his and my contact details up again at the end of this webinar. CDM Smith, they are a global engineering company, been around for quite a while. As you see, they're celebrating their 75th anniversary this year. They have their origins in the US and now have 5,000 employees worldwide, 650 of those being in Europe. So Reinhard has quite a lot of friends sat around him where he is. Now, obviously, today's session is purely theory. But if you would like to see the ABEM WalkTEM 2 in the field and get your hands on it, see how it works, then Reinhard is actually going to be doing 2 practical demonstrations of the system next week. The first will be in Hanover on June 21st, I believe that's Tuesday, and the second will be in Stuttgart on June 22nd, both running from 10 a.m. till midday. And if you're interested in those, then you can sign up via our LinkedIn page, or I will put the link into the chat. Yep, so you can jump directly to it. We will only allow people to attend who have registered because the demos will be done at customers' premises, and so obviously they need to know who's coming and how many people, just so they can make sure everything runs smoothly. So yeah, either jump onto our LinkedIn page, our website, or follow the link in the chat. So what is TEM and why would we want to use it? Well, TEM is a non-destructive inductive method that we use to map conductivity or resistivity. Most systems allow you to present in one or the other form. And by inductive, we mean that we're using a wire loop to transmit a signal and then coils of wire to receive signals coming back from the ground. So there's no need for a physical connection to the ground as we would with a traditional electrical resistivity measurement. That means that the field setup is pretty simple. So there's a kind of schematic of it down in the bottom right, a transmitter loop laid out around the outside, and then we would have one or more receiver coils at the center attached back to the instrument. TEM responds to conductive bodies. That's really where we are able to generate signals. And so for that reason, TEM is best suited to mapping things like groundwater, mineral deposits, or looking at indicators of environmental change, such as things like permafrost studies and how groundwater changes through the seasons. We can use this method as either a search tool, so just taking rapid measurements at very sparse intervals to identify regions of interest to then investigate more fully. We can close up the spacing between our soundings and use it as a mapping tool, and we can even use it as a monitoring tool as well. So we can actually set the system up to do repeated measurements, or we can return to the same site and compare how the resistivity models change over time. It's very rapid to actually take a measurement once we've laid the equipment out, and we've said that it's a relatively simple setup in the field. We're talking about a few minutes to take a sounding that could be, a few hundred meters deep. And so it means that we're able to actually get into site, set up, take a measurement and leave in the time that the nearest equivalent, that would maybe be a VES measurement, a vertical electrical sounding measurement, we can do that while that would probably still be halfway through or something. So it is a very rapid means of understanding the resistivity model beneath your feet. So how does the system work? Well, again, a very simplified schematic here. We have a transmitter coil laid out, or transmitter loop laid out around the outside of the area that we want to investigate. And we run an electrical current through that loop. And going back to school textbook physics, if we run a current through a loop of wire, then we generate a magnetic field around that wire. What we then do is we switch that current off very, very quickly, and it forces that that magnetic field to collapse. And because we can't just remove energy from a system, it has to go somewhere. So that collapsing magnetic field generates electrical currents in the ground, and we call these eddy currents, and they flow directly beneath the transmitter loop and then spread out into the ground, getting deeper and wider as they go. So quite often these are called smoke rings because of the way that they are propagated out through the ground. Those eddy currents that are in the ground are acting like a current flowing in a loop of wire, and so therefore they are generating their own magnetic field, and our receiver coil back at the surface is then measuring that field, measuring the eddy currents via their field, and we call that the secondary field. So primary field is coming from the transmitter loop, secondary field is coming from these eddy currents in the ground, and the way that those eddy currents decay over time tells us something about the resistivity or conductivity as we get deeper. It's not quite as simple as just sort of firing a current around the loop and then being done with it. We actually pulse the current very quickly around the loop, and we pulse it in an alternating pattern. So the current is pulsed forwards and then backwards, forwards and then backwards. And by doing that, we help to eliminate any drift in the measurement. We are not charging the ground up in one particular polarity or another. We are hopefully, by the time we finish our measurement, leaving the ground in a very similar state to how it was when we started. Unfortunately, it's not quite as simple as that initial drawing made out, with a nice square-shaped pulse of current switching instantaneously on and instantaneously off. We actually have a ramp of current building up in the loop, and then a ramp as the current is removed from the loop. And this is quite an important concept, because the faster we can remove the current from the loop, the better the pulse that we can generate, the bigger pulse we can generate, and also the quicker we can start measuring our response from the ground. And I'll come back to that in a moment. But basically, whilst the current is being switched off, that's when we generate the eddy currents. That's when the magnetic field is collapsing and these eddy currents are starting. And we call that an EMF, electromotoric or electromagnetic force. And it's a pulse of energy generated by that current switching off. Once the current is off, well, then we need to pause for a moment to actually listen, in effect, to what is happening to those eddy currents moving through the ground. So as those eddy currents spread out and get deeper, and that magnetic field gradually decays, we're going to record that through the receiver loop during an off period. And then once that's done, well, then we do our repeated current pulse in the opposite direction, and then take another measurement. And then we repeat and repeat and repeat, stacking many, many times to improve the signal to noise ratios. So I said that being able to switch the current off quickly was important because it generates a big pulse, but also because that defines how quickly we can begin to measure the effect of the eddy currents. So obviously those eddy currents are moving down through the earth, and we want to start measuring as soon as possible so that we can get information about the very shallow layers as best we can. But the problem is that if we have any current in our transmitter loop, so here's our pulse coming on in the transmitter loop, stabilizing and then being switched off, any current that is in that loop will still be generating a magnetic field that is far greater in magnitude than the field that is coming from the ground beneath the loop. So that means that we have to wait until all of that current has disappeared before we can begin our measurement of that secondary field. So the longer this takes, the further that eddy current or that transient has moved through the ground before we can start to record it. Once we've recorded how this field changes over time, we can actually convert that to an apparent resistivity or apparent conductivity from surface to depth. And we call it apparent because obviously if we're measuring from the surface, we don't know what different layers there are and how those layers are affecting the measurement that we've made. So we get a curve of apparent resistivity. We then put that into inversion software, and the inversion software will try and produce a model of resistivities that would create the same data that we have collected in the field. And then once we have that model of resistivity, so here you have depth down the side, resistivity across the bottom, and you can see how it varies with the different layers, then we can start to make our interpretation. And that'll either be an absolute interpretation where we look at the values that have been returned and look at published tables of resistivity for different materials and say, well, this seems to be this material, or as is more common, we look to do a relative interpretation whereby we say this appears to be the background value, and here we have a change, and I suspect that that change might be because of the presence of, for example, water or some kind of mineral body. Just for those who may be new to the methods entirely and not really that familiar with inversion, inversion is this process of going from our raw data to a model of the subsurface. So what we do is we take our data that we've measured in the field, so that's a series of data points gradually getting deeper into the ground, and we give that to the inversion software. So this is our apparent resistivity curve. We tell it how we've taken the measurement in the field. That's embedded in the header of the data file. And so the inversion software generates a model of what it thinks the ground might look like, and then repeats our survey over the top of that model. It then looks at how the curve would come back, the raw data would look if the ground had been like this. And if it doesn't match, which it never does on the first time, it'll then change the model and try again. And it'll keep changing the model until it gets to a point where it's either run out of attempts, it can't make any more models, it says, right, that's enough, I'm not getting anywhere here, or when the raw data that we've given it and the modeled data that it has created match very closely, and then it will say, right, here is a model, and this is what I think the ground looks like. At that point, it'll also present us with what we call a residual, and that is just a statistical description of how close the modeled data is to the raw data. So if you have a low residual, it means that the two apparent resistivity curves sit directly on top of each other very nicely. And if you have a large residual, it means that there is a big variation between the two. So theoretically, lower is better, but there is a big caveat on that, and that is that it has to be a realistic model. So when we get these models returned to us, we need to say, is this what we would expect over this particular geology or this kind of target? Are these realistic resistivity values that I have had returned to me? So there are lots of different models that could produce a very similar looking apparent resistivity curve, and the inversion software doesn't necessarily know what would be realistic for the site that you are working on. So it does take some experience and some analysis to ensure that the model you've been presented with is reliable. We can improve the models by putting in prior information. So if we have information about the depth to particular geological interfaces, we can help the inversion software by giving it that information. Or if other geophysical methods have provided us with information, we can add that into the inversion as well to try and improve the final result. This now starting to appear in some of the inversion packages is the option to extract IP effects from your TEM data. So IP is induced polarization, and this is where we look at actually how the ground charges up and discharges at the point where the current is switching on and off. So when we switch the current off, the voltage in the ground does not just disappear very rapidly, it will drop off at a certain decay. And that's to do with the composition of the minerals that are in the ground and chemicals that are within the ground, and also the structure of the ground, sort of how interconnected pore spaces are, for example, that would allow the current flow to be easier. So chargeability can give us a sort of extra tool for our interpretation, either by responding, showing a response for certain minerals that have a high IP effect associated with them, like sulfide ore bodies, or it could be clay. And these kind of differences allow us sometimes to differentiate between materials that otherwise have very similar resistivities. So a very common example is the big overlap in resistivity values for fresh water and clay. They actually have quite different chargeability values associated with them. So it can aid your interpretation to understand the chargeability as well as the resistivity model. So that's the kind of theory about how we're generating and recording signals. We'll talk a little bit now about the practicalities of designing a system or setting a system up, and what we can change in a system to make it more suitable to the particular targets or depths that we are trying to map. So the geometry of our transmitter loops and our receiver coils will affect how well we can image different parts of the ground beneath us. So if we start with the transmitter loop, if we make a bigger loop, then we can make a bigger pulse. So the larger the loop, the bigger the initial pulse, and the stronger the eddy currents we then generate beneath it. So that means that if we use a bigger loop, we should be able to achieve a greater depth. There is a payoff though. The downside of using a larger loop is that it takes longer to switch the current off. So if you imagine having a very long hose pipe and you turn the tap off as quickly as you can at one end, the water will not stop immediately at the far end. It will continue to flow for some time. And it's a bit similar with this. If we have a very long transmitter loop, it takes a long time for the current to stop flowing in it. I mean, when I say long time, I'm talking in physics terms. You know, you're not sat there watching your clock waiting for it to happen, but it does impact how easily we can map the shallower layers because we can't start the recording for longer. When it comes to the receiver coil, well, then the size is defining how quickly we can respond to the changes in that secondary field. So if we use a very small loop, it can respond very, very quickly and therefore can map the eddy currents that move very fast near surface very easily. The problem with a very small receiver coil is that once those eddy currents get deeper and the secondary field is much weaker, that small loop, that small coil isn't scooping up as much of the secondary field and therefore struggles to record it when it's much deeper. So if we use a larger receiver loop, then we can record the weaker, slower moving responses from depth much more reliably, but we do so at the cost of the near surface detail. So let's have a look at how that transient moves through the ground. And what we're looking at here is, again, a very simple schematic of the ground surface with our transmitter loop and a single receiver coil at the center. And then what we've got beneath is a representation
of this eddy current that is flowing in a kind of circular pattern beneath the transmitter loop. So red here indicates that it's coming out of the screen towards you, and then it's swooping round, and then blue is where it goes back into the screen. And so what we see here is that the eddy current is spreading outwards and downwards, but never leaves contact with the ground surface. It's always touching the very top there. So what does that mean for us? Well, it means that we're measuring a huge volume of Earth in here. So we are not going to have particularly precise detail when it comes to lateral measurement. So, you know, this is a 1D method. So by definition, you know, we are really only interested in the vertical changes in resistivity. And that's just as well, because as I say, we're measuring a huge volume here. The angle at which that eddy current spreads out is about 30 degrees. So if you imagine having a 40-meter loop at the surface, by the time you're, say, 100 meters down, that eddy current is huge, absolutely huge. So we're encompassing a large amount of geology when we do these measurements. Now, at the moment, this is a bit of a false impression of how an eddy current or how a transient moves through the subsurface, because we're plotting it with a log time sample. So if you look at how the time increases on the top left of this diagram, you'll see that for the first few slides, it's increasing 1 microsecond at a time, and then it jumps to tens, and then 50s, and then hundreds, and then thousands. So we are slowing down the very initial part of the transient's movement and kind of speeding up the very late time. So if I plot this now with equal time for each slide, so this is what it would be more like in reality, then you see that those shallow responses are incredibly fast and the deeper responses are much slower. And this is what makes TEM quite a difficult method to design hardware for, because we have to design a system that can record large and very fast changing signals very early on, but also record very small and very slow changing signals later in the decay. And we're still only talking about a couple of thousand microseconds. So obviously this is, you know, happening in a fraction of a second. So it's a very difficult thing to design electronics to be able to do this reliably. So there we were looking at a 100 ohm meter model. We're going to go back now to using the log plot of the time, just because it's a bit easier to see what's happening with the transient if we do that. And what we're going to do is we're going to compare a half space with a very low resistivity with a half space with a higher resistivity. And both of these transients start at the same time. So these two images are, or animations are paired. And what we see is that in the higher resistivity, the transient moves more quickly. So it spreads out much more quickly there. Whereas in the low resistivity model, it hangs around at the surface for quite a bit longer. And this is why TEM is most suited to detecting and mapping conductive bodies, because the transients will hang around in the conductive areas, whereas they will move very quickly and decay quickly within the resistive areas. We now look at a two-layer model where we have a low resistivity at the top and a high resistivity at the bottom. What we see is that the transient again hangs around in that low resistivity top layer and doesn't really penetrate particularly well into the higher resistivity bottom layer. If the opposite is true and we have higher resistivity above lower resistivity, well, then the transient moves through that higher resistivity and then transitions very easily into the more conductive body below. So again, this is reaffirming the fact that this method is well suited to identifying these conductive bodies, because if you imagine that this was some mineral ore or an aquifer within a resistive bedrock, then clearly we're going to be able to identify that very well. Whereas if we were trying to map a resistive layer beneath a conductive overburden, it would be very difficult for us to absolutely identify what the resistivity of this bottom layer is. So you'll find when you do inversions with TEM, if you come to a resistive basement, the point at which it hits the contact between the more conductive overburden and that resistive basement, that contact depth should be defined pretty closely. It should work quite well. But the absolute resistivity of that basement will be difficult to determine, and it will generally have a low reliability associated with it. And the reason for that is that once a layer goes maybe above 200 ohm meters, something like that, it could quite easily be 2000 ohm meters, and TEM would not differentiate between the two of those when you run an inversion. All TEM knows is this is resistive. It can't identify how resistive it is. So again, reaffirming that this is a method for identifying conductive bodies rather than the absolute resistivity of resistive targets. That can cause us a problem if we have a resistive layer trapped between more conductive layers. So here we have a 4-layer model with a resistive overburden, a conductive layer, another resistive layer, and then another conductive layer beneath. And what we see here is that the transient moves through the first resistive layer, relatively easy to model that. It sits in the conductive layer beneath in layer 2 for a while, so it's quite easy for us to model that, but it skips layer 3. It basically jumps that layer, doesn't hang around in it, moves through it very, very quickly and leapfrogs it into the more conductive layer 4. And that causes us a problem because we don't really have any data points, don't have any reference measurements for that 3rd layer. And so effectively it disappears into our model and we don't really see it when we run the inversion. So here we can see we've basically got layer 1, transition, layer 2, transition, layer 3. So in the raw data, we are only really seeing the effect of 3 of the layers, and that middle one there is kind of lost to us. So again, reiterating, it isn't the ideal method for resistive targets. So that's the question then. Well, how else? What else should I consider when I'm deciding whether or not I want to use TEM for my measurements? Well, I would say that 4 questions are all you need to ask to understand whether or not TEM will be suitable. So the first one is, what is the application that you're going for? You know, what is it that you want to map? And so good answers will be, as I say, anything that's conductive. So groundwater, saline intrusion, salination of groundwater, areas of mineralization, or looking for bodies, other bodies that have particularly high conductivity associated with them, such as clay layers. So less ideal would be, hey, I've got a resistive layer of stone that I want to extract and I want to know where that is. Well, then that wouldn't be an ideal target for TEM, and you would probably be better off looking at something like VES or ERT. Target depths. Well, TEM can actually penetrate very deeply. The only thing really that is limiting you is the size of the loop and the amount of current that you can put around it. So for our WalkTEM system, we would say that anything under 600 meters is relatively easy for us to achieve. Once you get over 1,000 meters, that is probably pushing the limit of what we would be able to map. ABEM traditionally are near surface geophysical instruments, and I think that once you get beyond 1,000 meters, we can probably ditch the near surface titles. So yeah, that's the kind of range that we're working in. TEM, like VES, is a 1D method, and so therefore it is better suited to the measurement of horizontal layers, looking for vertical changes rather than lateral changes in the structure and composition of the Earth. So if the target that you're going for is particularly confined laterally, then it might not be the best choice of method, because it is just 1D. And as we said, we are mapping a very large volume of Earth pretty quickly when we do a TEM measurement. So again, something with a bit more detail like ERT might be the better option there. And then where would you be working? Well, TEM does have one slight drawback with it, and that is that it's very prone to noise from conductive man-made structures. So buildings, pipes, cables, that kind of infrastructure can be particularly problematic, because what happens is that we tend to induce signals into those conductive man-made structures as well as the ground that we're interested in mapping. But as far as the TEM is concerned, it doesn't know that there are man-made structures around, and it can only assume that the conductive targets that it's seeing are beneath it in the ground and some kind of natural feature. So then when you do the modeling, when you do the inversion, you'll have a very skewed model because of the response from these man-made structures. So there is a rule of thumb that we use, which is that you will have your transmitter loop, and the nearest piece of infrastructure should be at least twice the loop side away from you. So if you're using a 20-meter sided loop, 20-meter square sides, then the nearest piece of infrastructure should be 40 or 50 meters away. If you're using a 40-meter loop, 80 to 100 meters away. 100-meter loop, let's say 200 to 250 meters away. So it's not really designed, or it's not really suitable for using within urban settings. So mentioning noise there, there are a whole source of noises. Fortunately, most of them we can actually get rid of during the measurement or at the processing stage, but there are some that are more problematic. So we have electromagnetic noise. This is noise that's in the environment all around us, coming from things like mobile phone communication, radio, TV transmissions. It could be coming from electrical installations, so the national grid network, railway networks that are leaking voltage into the ground. And so there are two different types of electromagnetic noise, coherent and random. Coherent means that it's a pattern of noise that repeats and is always the same. Random, as it suggests, constantly changing. So the electrical installations, they are coherent noise. They are happening at a particular sinusoidal pattern at a particular frequency that we will probably know. The electronic noise from communications, that's random, changing all the time. So the coherent noise from installations, we can actually remove during the measurement process. So when we measure the decay in a TEM measurement, we don't measure individual data points, we actually measure in time windows. So we integrate over a period of time and then have another time window, another one, and another one. And they gradually get longer as we get further into the decay, and we need to measure for longer to get a more reliable result. If we make those time windows the right length, then there'll be an equal number of positive and negative pulses from the electrical installations within that time window. And so when you do the integration, they cancel themselves out and disappear completely. So they're very easy to get rid of. We do that with the scripts, the measurement scripts. And then the electronic noise we remove by stacking. So we repeat the current pulses hundreds, if not thousands of times during a single measurement cycle. And that allows us to effectively cancel out a lot of the background noise, whereas the true signals that are coming from the ground just superimpose themselves, and our signal to noise ratio increases. We then have natural and sources of noise. So the first one, environmental noise, this is basically more EM. And it's coming from what we call spherics. So this is electromagnetic interference from solar flares, solar winds, radiation from outer space coming in and interplaying with the Earth's atmosphere, and then fluctuations within the Earth's magnetic field as well. And they generally cause just random noise. And again, so we can remove that, or at least reduce its effect by stacking. Then we have what I've called natural geological noise. It's not really noise, it's more deviation from the assumptions that we make when we do a 1D measurement. So our assumption for a 1D measurement and then producing a model, an inversion model, is that whatever we see in the data, we are seeing horizontal layers, and those horizontal layers are homogeneous, so they don't change resistivity in any direction, and they remain horizontal to the horizon. There are very few geological scenarios where that is actually true, but a lot of geology will meet it to a close enough degree that the model that we produce is reliable. The problem with that is that if that assumption is not met, it's a coherent source of deviation. So that bit of geology, let's say we're taking a 1D measurement here, and we've got relatively well-defined layers of distinct resistivities, but over here there's a large either conductive or resistive body. That transient will pass through that conductive / resistive body, and so that will impact the measurement we make. But we have to assume when we do a 1D measurement that whatever we measure is coming from directly beneath the loop, and it might be off to one side, and every time we repeat the measurement, that geological feature or whatever it might be that's causing that deviation is still going to be there. So that is a difficult one that we can't necessarily deal with, and we just need to be aware of the environment that we're working in and whether there are likely to be these kind of changes. Then we have instrument noise. These are separated into sort of two different categories. Just random noise that comes from small electronic fields that set up around the individual components, and then bias, whereby slight deviations in the manufacture of individual components set up an offset in the measurement. And again, fortunately, we can get rid of both of those, the random noise by the stacking process and the bias by calibrating systems. So we take a set of measurements, compare it to a reference set of measurements, change the calibration values in the instrument such that it will then produce the same result as the reference. And then the final one is where we actually started with this discussion, and that's this coupling. This is where we're generating signals in man-made structures that are either beneath or around us when we take the measurement. And again, this is a problematic one because it is coherent noise. It is noise that every time we take the measurement, we will get the same response from that particular piece of infrastructure. And so therefore we can't remove it from the data. So that means that we have to sit there, have a look around us before we start a measurement and say, is there any infrastructure here? Is it close to us, so close that it's going to cause a problem with our measurement? These two types, there's this capacitive and galvanic. Capacitive is actually the better noise, if you can have such a thing, just because it's very easy to see in a data set. Your decay curve should always be a nice smooth curve. And if it suddenly starts jumping around, that's usually this capacitive coupling that we get. And so you can see that and you say, oh, right, there is something wrong here. Let's move, let's check the equipment and then try another measurement. The galvanic coupling is more difficult to see because this is when you have some conductive body, it has a good earth on it. And so you just generate an eddy current in it and the eddy current slowly decays because that then replicates in a very similar way a conductive body beneath the ground. And so in this particular example, what we're seeing are two soundings on the edge of a settlement. Sounding one is sufficiently far away from these buildings to not be affected by coupling, and sounding number two is a bit too close. And what they've actually been impacted by here is this galvanic coupling, this electrical coupling, which has generated eddy currents in something, probably a metal fence or something similar that surrounds these houses. And so that's increased the electromagnetic fields, the secondary field that we're measuring. And the result of that is that if we look at S1, we've got a decay that ends up much further to the left in the time scale than S2, which was nearer the infrastructure. So the curve has been pushed out to the right-hand side, and normally that indicates something conductive because it means the eddy current is hanging around somewhere for longer. If you then were to run an inversion, then what we see is that on the resistivity model, S1, which is the true scenario, shows a very simple model of overburden and then some kind of bedrock unit, whereas S2 shows something very conductive at depth, and in reality, that's not because of something beneath the ground, that is because of this coupling effect. Okay, so that's all the theory. Let's now have a quick look at some just example data sets, and then we'll move on to the WalkTEM 2 itself, the instrument, and then we'll finish off with some questions at the end, if there are any. So this first one, a very small data set, very simple. In a lot of Scandinavia, they have problems with a material called quick clay. So this is clay that has a very high salt content. It's a marine clay, and you find it in layers in the geology. And when that clay has its salt still in place, the salt adds structure to the clay, makes it nice and firm and stable. But what happens over time is that gradually the salt is washed out of the clay, leached out of the clay, and when that salt disappears, the structure of the clay disappears and it produces a slip plane. And so there was one in the news, oh, it might be a couple of years ago now, given the compression of COVID timescales, that was in Norway, where an entire hillside basically slipped away, and that was due to this quick clay. So it doesn't take very much to actually start the ground moving. So quite often it's associated with construction work, and like a bit of vibration in the ground causes this clay to liquefy, and everything that's above it then just moves. So the good thing is that the clay is particularly conductive, so it's a good target, and the salt clay is even more conductive. And TEM is excellent at being able to identify the difference between two materials that are very conductive themselves, whereas a traditional electrical resistivity method might, when you run the inversion, it might struggle to say how conductive a particular body is. It will just know that it is conductive, whereas TEM can actually differentiate. So this is just one sounding from a sort of landscape scale survey where they've gone across taking soundings at a lot of locations, just trying to map where the quick clay lies and whether it's still salt laden or whether it's got areas where the salt has been washed out for whatever reason. So here is the, on the left-hand side, the decay curve, the sounding curve, with the dots in it representing the raw data and the solid line representing the modeled curve. So this model here with resistivity in 1, 2, 3, 4, 5 layers produces the curve that you see fits very well with that the raw recorded data. So on this side, we've got depth down the side, resistivity across the bottom, a green line that shows us our DOI, our depth of investigation. So below that, the model is sort of unreliable. And what they've highlighted with the circles are the areas where the clay is less conductive, more resistive. So we've got clay probably from whatever that is, sort of 2 or 3 meters below the surface, down to 20 something, 30 meters below the surface. But the very top and the very bottom of that clay unit show a slightly higher resistivity, and that indicates that perhaps the salt has been washed out of the clay, and therefore these regions could be at risk of slipping. And so it's a very quick way of getting across the landscape and taking these measurements. For this kind of scale of survey, they're probably talking about a single small transmitter loop, like a 20-meter transmitter loop, a single receiver at the center, and taking a measurement that might take 4 or 5 minutes to collect the data. So maybe 10, 15 minutes to lay the loops out, 4 or 5 minutes to actually undertake the sounding, and then you're ready to move on to your next location. So you can be very productive in a single day. And moving on to sort of TEM's kind of what it's particularly good at, which is groundwater. And this first example is just one, again, a bit like the previous example, where they were trying to just search and map the presence and extent of aquifers. This is in East Africa. You can see that the ground surface is particularly dry and cracked, so it wouldn't be much fun doing a traditional ERT survey here because you would struggle with contact resistance on the individual electrodes, or even a VES survey. And they took, I can't remember how many, hundreds of soundings across a very large area of this particular region of East Africa. They were using the WalkTEM with a 40 by 40 meter transmitter loop, 2 receiver coils at the same time, one to receive the, one tuned to the shallow, fast changing transient, and one slightly larger, which is better at receiving the transient secondary field when it's much deeper and slower moving. And so these are just some examples of the models that they generated, and they have a very good understanding of the range of resistivity values that indicate fresh water in that particular geological setting. So they know the host rock plus water makes for resistivities within a fairly narrow range of values. And so they simply would undertake their soundings, highlight the region on the model where the resistivity is within that region, and use that as the indicator of the presence of an aquifer. With this one, they were also able to identify in some locations where the aquifer becomes saline at depth due to mineralization, or perhaps recharge from the coastal region being drawn in rather than it being recharged from surface water. So again, this is where the resistivity drops to an incredibly low value, around 1 ohm meter, which just indicates that there must be saline water within the geology. This site, we use this a lot for as a case study because it was kind of ideal conditions, very homogeneous, slightly resistive overburden, which then gives way to a conductive body, large conductive body, i.e. the aquifer. So the transient moves very rapidly through the resistive overburden, gets into the conductive bit below, and sits there for a while. So that meant that with that 40 by 40 meter loop, they probably hit what would be considered the maximum achievable for that. 40 by 40 using somewhere between 7 and 15 amps around the loop, and their DOI that they got back from the inversion was between 300 and 450 meters deep, pretty consistently across that region. So I would say that's pretty much the maximum for that kind of setup. If you're somewhere where you've got more conductive materials throughout the half space, then you're going to see a much shallower DOI. This one is using a slightly larger system, and also rather than just taking individual soundings, this is closing the spacing between the soundings to generate some 2D profiles. So this was in the Middle East, and you can see down here, this was done as a bit of a pilot study for someone who was considering whether or not TEM would be useful for them. You can see just a number of soundings undertaken in 2 profiles across this landscape. And they were using primarily the WalkTEM with an external high power transmitter, 60 amp transmitter, with a 100 by 100 meter transmitter loop, so square with sides of 100 meters, enclosing 1 hectare of land. And then they actually used 2 receiver coils at the center again to be able to map both the shallow fast changing transient and the deeper slower moving one. And they were using 96 volts to drive 60 amps around that loop. So they had, what would that be, 8 12 volt car batteries there to power the system. So this is just one example of the sounding of the model that they got back from one of the soundings. And then on the right hand side, what you see is how they can generate that into a 2D profile. And this is using a piece of software called Aarhus Workbench to do what's called a laterally constrained inversion. So it's a little bit better than just interpolating between individual soundings. It actually takes into account what's happening in adjacent measurements to determine what should happen between the different soundings. So this is the 2D profile, with the purple being the highest resistivity and the greens, yellows and reds being the lower resistivity. And what we see is that we have a clayey, silty layer quite deep, over the top. And we drop into the sort of bedrock area, and that's pretty high resistivity, and it remains high resistivity until we hit the aquifer at depth. And the reason why they wanted to do a pilot here was because the aquifer is known to be particularly deep in this region. So we can see that, I don't know how well you can see it on your screens, but these are elevations above sea level. So basically the top, the surface where they were taking the measurements was about 1,000 meters above sea level. And the top of the aquifer is about 500 meters. So 500 meters below the surface. And the DOI was around about 800 meters for most of the soundings in that particular location. So again, relatively good environment for doing measurements, with, again, a pretty homogeneous, relatively resistive chunk in the middle, and then something conductive at depth. And then this next one is actually one that is used as an example data set with the Aarhus Workbench software, which is the sort of processing software that we generally recommend. We use Aarhus Sphere TEM for doing the 1D inversions, and then Workbench for doing further visualization. And so in this particular example, it's looking for river channels. So this is actually in Denmark, where the groundwater is all stored in paleo channels, old river channels that are full of sand and gravel. So that acts as a natural sump, a natural reservoir for the water, because in Denmark, pretty much all of the geology is clay, and so it doesn't really hold water in any great volume. So that's what they're trying to map. So this is an example data set. So if you want to have a play around with Sphere TEM and Workbench, you can actually ask for a trial license. You can download this data set and you can work with it. And what we see here are the black dots of the individual soundings. There are 16 soundings in total along a transect, which is 1.5 kilometers long. So the soundings were taken down one line, down to the bottom. It's hidden behind this image. Turn around, come back up again. And that was easily done in a day with a team of sort of 2.5. And I know that because I collected the data. So there were two of us with the 40 by 40 meter loop and the small receiver coil at the center. And then we had a third partner who was driving a vehicle, dropped us off here, drove round to meet us here. And then we went across these fields and they dropped us, came and met us at the far end again. So very easy to achieve that amount in a single day. We weren't really pushing ourselves at all. Again, just because of the ease of layout and the speed of data collection. And then once you've done that, then you can actually start to generate either 2D profiles like we looked at before, where we see the conductive clay in blue and the sands and gravels that contain the water being a bit more resistive with the reds and the purples. Or we can actually slice through the data from the surface down to give us maps of resistivity at different depths. And so there we can see the river channel coming through the middle here. And if we could see the bottom end, you'd see that it was back to blue in the clay over this side. So very easy to map the shape of the channel and therefore work out the volume of material that would be held within it. Okay, so for the final bit of the actual presentation, I'm going to look at the WalkTEM 2, the current offering that we have for a transient electromagnetic system at ABEM. The WalkTEM 2 was launched in, I think it was February last year. So it's been out about a year and a bit now, and it's quite a step up from the WalkTEM 1 in terms of it's a slightly different design. So our WalkTEM 1 was transmitter and receiver electronics all in a single box. With the WalkTEM 2, we've separated out the transmitter into a separate box because we wanted to put a bit more current into the transmitter, allow it to be a little bit more powerful. And we didn't really think it was realistic to be able to record good, clean data with that more powerful transmitter sat right next to the receiver circuits. So we've separated them out now. We've also increased the number of models so that hopefully people find it an easier fit. With the WalkTEM one, there was only really one model, and then the only way you could really change the design of the instrument was to change the loop sizes or add a high power external transmitter. So now we've got a few more options for people to consider. Main components of the system, as I say, we've got the receiver unit that's recording the secondary field from the eddy currents with a maximum of 2 channels. So we can either have 2 different size loops, or we can have 2 loops the same size in different orientations if we want to measure different components of that secondary field. We then have a choice of external transmitters that can then power our choice of transmitter loops. So looking at the receivers themselves, there are 2 different options. There's a standard and an advanced receiver. They actually are exactly the same machine in terms of what's inside them. So all of the hardware is in both the standard and the advanced. The specification is controlled by a hardware license, which means that if you were to purchase a standard and later decided that you wanted some of the more advanced features, you can pay for the upgrade and then immediately have the benefit by just connecting online and having the license upgraded. So there's no need to send the instrument back to Sweden. Our advanced is, as I say, it's a 2-channel instrument with a choice of 2 receiver coils, a choice of 3 transmitters, a very wide range of transmitter loop sizes. We have onboard inversion. So we have processing software built in. This SPEAR TEM is built into the software so that you can actually do an inversion on the machine as soon as you finish the data collection while still in the field. We have the ability to do waveform analysis, and I'll talk about that later. We have a dual moment operation, which again, I'll talk about in a few minutes, which is where we can pulse both high and low current signals through the transmitter loop. We have internal damping resistors, which I'll talk about again in a moment, to tune the transmitter loop to give us hopefully a perfect transmitted signal. And we have hot swappable batteries, so just slide in, slide out lithium-ion batteries. So that's the advanced. If you buy the standard, the difference is that you only have 1 measurement channel, so you can only use 1 receiver loop, and you can only use what's called an RC5. That's the smaller of our receiver loops. So we have 2 different sizes. It only works with the smallest of the transmitters as well, and it'll only work with the 2 smallest loops. There's no onboard inversion. You can look at your raw data, but you can't create a model from it. You have to take the data off onto an external PC and then process it. The waveform analysis is an option on the standard, but the rest, the dual moment, the internal damping resistors, they are the same. So as I mentioned, the receiver coils there, like I say, there are 2 different sizes. There's a small RC5, which is about 1/2 meter across. It's got 20 turns of wire in it, and it's the equivalent of a 5 meter square loop. So that's the one that is very good for the shallow responses and the one that we would use with the smaller transmitter loops. And then the RC200 is a flexible 2-turn 10 meter square that we would prefer to use for deeper measurements. So it's not compatible with the smallest transmitter. It wouldn't really fit inside it very well. But as I say, on the larger loops, we can actually use both together. In terms of transmitters, we have 3 options: TX8, TX20, TX60. So 8 and 20, the 8 just means that the maximum output is 8 amps, 20 amps. So this is limited for the shallower applications, and obviously is an entry level kind of cost for that one. Like the receiver, this transmitter unit has the same hardware in it, regardless of which you buy. And the specification is again controlled by a hardware license. So you are able to upgrade later, again, without having to send the device back to Sweden. We can do that upgrade remotely for you. If you need to go above 20 amps, well, then we have a separate, much larger transmitter, the TX60. So this has the ability to output 60 amps. And the only downside of that is that the larger transmitter doesn't have a dual moment operation. So dual moment means that it can alternate between putting out a small current and a high current. The TX60 will just put out the maximum it can for the voltage that has been applied to it. Then we have a range of transmitter loops ranging from 20 by 20 meters up to 200 by 200 meters. And again, you're really just defining how deep you can image by using the larger loops. And those two smaller ones are the only ones that are compatible with that standard receiver. So these are kind of the main combinations that you'd have: a standard receiver with a TX8, an advanced receiver with a TX8, an advanced receiver with a TX20, or an advanced receiver with the TX60. These first three options, you can jump from one to another remotely, upgrading remotely. This end one is actually, adding that additional box to the system. So what's happening as you move from left to right is basically you're going to be adding more features and being able to go deeper. So if you go from a standard with a TX8 to an advanced, you've still got the same high and low current capability, but you now have the additional channel. You can use all of the transmitter loops. You can use both of the receiver coils. You have the waveform analysis that we'll talk about in a moment. And you also get the onboard inversion. Then if you go from the advanced TX8 to advanced TX20, it's the same instrument. All you're doing is enabling yourself to have more power, generate a stronger eddy current, and hopefully see deeper. And then again, with the TX60, you are again increasing the maximum amount of power that you can output. So if you have a look at a couple of configurations, we have the RX standard with the TX8, so the basic receiver, the smallest transmitter, the smallest loop, the single receiver at the center, and that's kind of the entry-level model. That's the smallest system that you could buy. Depth capability probably around about 100 meters with that particular system. So excellent for any shallow application. Anyone who really, wants to try TEM but doesn't want to invest hugely to start with, then they can purchase this. And if they find it's doing what they need it to do, but they have a requirement for, say, more depth or more features, then they can upgrade. And also, if you have a limited budget, this is a good entry level to then upgrade at a later date, spreading your investment as you go. Largest configuration that we could make would be the advanced with the TX60, the 200 by 200 meter transmitter loop, and the RC200 at the center. No point using the RC5 with this setup because the RC5 is tuned for the shallow responses. You just can't switch off 60 amps running around a 200 meter loop fast enough for the RC5 to actually be useful. So you just use the larger receiver loop. With this one, I've said maximum achievable depth should be 800 plus meters. I've said that because we know from that Middle East example that the 100 by 100 with the TX60 was achieving DOIs of 800 meters thereabouts. So this should certainly be able to achieve that, and potentially down to 1,000 meters. So this is for those projects where you have a big depth requirement and you just don't need to know what's happening near a surface. So just to cover off a couple of the things that I mentioned on the functionality of the instrumentation. One was the dual moment measurement. So what we said was that when we're taking a measurement, we can't begin recording the secondary field until all of the current has gone from our transmitter loop. So a high current transmission, high moment, high pulse will give us the deepest response, but it will give us the longest switch off time. And so therefore we lose some near surface information. If we can then have a low moment, a low current pulse, well, then it's quicker to switch off and we achieve more information near surface. And even though that's quite a short time, it looks quite a small gap, we know that transient is moving very quickly, and therefore there's actually quite a lot of information encompassed in that short time. So what the WalkTEM can do is it can alternate automatically within a single measurement cycle between the high and low moment, and then combine both data sets to produce a seamless decay curve. And what it will do is pulse forwards, backwards, low moment, forwards, backwards, high moment, forwards, backwards, low moment, basically giving us hundreds or thousands of individual stacks, individual current pulses to record from. And that's not all we have. I mean, we have the low and the high moment. We would also potentially then have the decay curve from both the small and large receivers. So we have 4 data streams: low moment and high moment, small receiver, low moment and high moment, large receiver. And all of that is presented in a single data file that we can then filter and run the inversion on. And then we have the waveform analysis. So waveform analysis is looking at what happens when we switch that current off in the transmitter loop. So what we need to discuss briefly is the concept of damping. So we have our current flowing round a loop and we stop it very, very quickly. And when we do that, it generates noise, generates this oscillation of current and voltage around the loop. The way to think of it is if you imagine a gutter of water that is flowing at a constant rate. If I was to suddenly stop that flow of water in that open pipe, there'd be a big splash. So that's our EMF pulse. But then there would be waves kind of splashing backwards and forwards through the pipe. And that's kind of the problem we have when we try and switch this current off. So what we need to do is we need to be able to damp that. We need to constrain that oscillation backwards and forwards. And we need to be able to damp it at kind of what we call the sweet spot, where we don't over damp, because if we put too much damping in, we don't generate a nice big pulse. But if we don't put enough damping in, we end up with this kind of oscillation, this noise that then gets carried through the transient into our raw data. So we do this damping by applying damping resistors to the transmitter loop, and the damping resistors are built into the transmitter on the TX8 and the TX20. So we just need to select the correct one. And for example, on the WalkTEM 1, choosing the correct damping resistor was entirely manual. You had to take a measurement with one of the damping resistors in and look at the raw decay curve and say, yay or nay, yes or no, do I think this is good or bad? And then if necessary, change the damping resistor and look at it again. And it's a very subtle difference in the decay curve, but that subtle difference in the decay curve can generate a huge difference in the final model. And even for an experienced TEM user, sometimes it could be quite difficult to decide which damping resistor was best. And quite often what people would do is just take 2 measurements, one with each, and then process both of them. We now use what's called a Rukovsky coil to actually do a test measurement where we run current around the loop, switch it off, and have a look at the decay, have a look at the switch off point. That's the very first bit of the decay where we first switch off the current, and look at what happens in the transmitter loop rather than in the receiver coils. So the Rukovsky coil is measuring that removal of current, and it will do it for all of the different damping resistors, and it will show us a plot of the current switch off for each one. And so what we're trying to look for is the one which switches off and comes back to 0 current the quickest, but does so without then bouncing up and down. So we can see one there that has an oscillation in it. So we know that that's not one to choose. And we can see that there are some which decay or come back to 0 a little bit slower than others. So we would know that, you know, those ones have got too much damping on them. So now it's much, much simpler for customers to make sure that they have tuned the transmitter loop to the conditions that you're working in, because that oscillation, the rate at which it happens, the scale at which it happens, and the amount of damping that is required is based on the interplay between the transmitter loop and the ground beneath it. So this Rukovsky coil and the analysis tool, they are included on the RX Advanced, and they're an optional extra on the RX Standard. Okay, so that's everything that I wanted to cover today. I would just finish by reminding you that we have the 2 demonstrations for those who are in Germany. We actually opened up this webinar to everyone to come and join in, but for those of you who are in Germany, the demonstrations will be happening next week in Hanover and Stuttgart. I will just once again put in the link for registration onto the chat. As we said, only people who have registered will be allowed to attend. So you won't know where the event is happening until you have registered, and you'll get sent details. And that's just because it's happening at someone's premises. And so they, quite rightly want to know who's going to be coming to see them, how many people are going to turn up, so they can plan for that. So next week, Tuesday and Wednesday, I think it is, Hanover and Stuttgart, and it will be my colleague at CDM Smith, Reinhard Schultz, who you'll meet there. I think my colleague Peter might be there from Guideline Geo as well. And yeah, so you can use that link in the chat to register, or there's a post on LinkedIn for it as well. So I'm going to have a quick look back through the chat and just see if there were any questions. No. And I'll ask then, in that case, I'll open it up and just say, does anyone else have questions that they'd like to ask right now? Okay, well, I know how this works. I've sat through enough webinars and lectures where I always think of the question just after it finishes. Oh, here's one last question. Is it going to be a problem if any conductive matter is on the surface like vehicles? Yeah, vehicles could be problematic. So you would usually try to park them, the rule of thumb distance away. So if you're using a 100-meter loop, park your vehicles about 200 meters away just to be safe. As I say, I know how this works. Quite often you come up with questions after as soon as the session ends. So those are my contact details and Reinhard's contact details. So if you do have questions, please feel free to contact us. And if you have any problems with booking onto the demo days as well, you can email us and let us know, and we'll sort things out for you. So all it remains for me to say is thank you very much for attending. And I hope to see you at another webinar very soon. And for those of you who do go to the practical demonstrations, I hope you have good weather, and I hope you enjoy looking at the instrument. Thank you very much.